let us do the actual diamond structure. Okay. See, you just take atoms at all the cube corners as well as the face centers. There are 6 face centers: left face, right face, top face, bottom face, front face, face behind. These crosses are all face centers of the 6 faces. Okay. Now, suppose say this is the body center, which of course I am not marking because it is not part of this. Face center does not play any important role here, but its position is somewhere here. See, if this is say 0 0 0, suppose this say this is 0 0 0, suppose this is 1 1 1, then what will you call the body center? It is half half half, exactly midway between 0 0 0 and 1 1 1. This is half half half. So, if suppose this is 0 0 0, this is half half half. What should I call this one? This midway point between 0 0 0 and half half half. It will be 1/4 1/4 1/4, because it is 0 0 0 midway between 0 0 0 and half half half. So, this is 1/4 1/4 1/4. Just I select that point, say another cross. I have selected this point which is midway between 0 0 0 and say this one half half half, which is the body center, which is not shown here. This is 1/4 1/4 1/4. Yes. Now, join this. See, this is a unique orientation which is along say the body diagonal. Okay, it is somewhere here. Right. At this unique vertex, 3 faces meet: top face, left face and face behind. Take their face centers. Face center of top face is this, face center of left face is this, face center of both say face behind is this. Join them. See these blue lines. Okay. One can easily show that this will make a tetrahedron, say, which imitates this bigger tetrahedron. See, it is a tetrahedron along this one, along this lobe. Okay. Say, remember this involves A, the vertex A. Now, do similar thing for B, C, D, that is the diamond structure. See, now one can methodically do it, which is B. This is B, B. Just like you have 1/4 1/4 1/4 point here, you have another 1/4 1/4 1/4 point here, which is midway between this and the body center. Okay. So, shall I mark it somewhere here? It is midway between, yeah, it is somewhere here. Right. join as usual, just like what we have done here, do it. Then 3 faces meet here. Which are the face centers? See, face center, see the faces which meet here are bottom face, left face and front face. Take their face centers. Bottom face, face center, left face and front face. Join them. Right. See, now I think we gain more confidence because it makes a pattern. Just push it to its logical conclusion. What we have done with respect to A and B, you do also with respect to C and D. Which is C? C. C. Okay. Then join the, say, if you I mean if this is the half point, what is the midpoint between this and this? It is somewhere here. Yes. Join it. 3 faces which meet at C. Right face, top face and front face. Their face centers. This one and this one, join them. Right. Yes. Now we have almost completed. Now one more, the last one, last of the 4 things, namely along D you have to complete. So this is D. D. Then this is the body center. Yes. And so the 1/4 point is somewhere here. Yes. Then join it. Yes. You say now again mark the face centers of the 3 faces which meet at this point. The 3 faces are right face, face center, then bottom face, face center, and face behind, okay, face center. Right. So this is a diamond structure. Just compare it, say, with figures given in any book on solid state physics. This is a diamond structure. See, it is, the whole thing is a tetrahedron. So this thing is a tetrahedron, but each lobe of it has associated with it one tetrahedron each. One tetrahedron, first tetrahedron, second tetrahedron, third tetrahedron, fourth tetrahedron, 4 tetrahedra, okay, making a super tetrahedron. This is the diamond structure. Okay. Each of these is making an angle 109 degrees 28 minutes. The famous tetrahedral angle, the angle between sp3 hybridized orbitals. As you know, in diamond, carbon orbitals are 1s2, 2s2, 2p2. This forms a closed circle 1s2. The next 4, 2 plus 2, 4. Okay, they form hybridized orbitals. They are disposed or oriented along directions like this. These are the hybridized orbitals. Their directions are along body diagonals of the cube. See, this in fact explains the exceptional toughness or hardness of diamond, because it's, say, it does equal justice to all directions. Okay. See, it is quite clear. See, if a particular direction is chosen, its diametrically opposite thing is rejected, okay, and say it gives maximum, say, scope for all directions, and again covalent bonds are the relevant bonds here. Since these tetrahedra are accommodated inside a cube, okay, it is something like maybe the popular analogy I will quote. See, if you have Indian rupee, you may find it difficult to get it cashed in any other, in any country, but you just convert it into dollar. It is something like an international currency, okay. So, you find it very easy to convert, say from one currency euro to dollar or pound or say some other currency or rupee, whatever it is, okay. In this way, see, the strong covalent bond which remains at the molecular level in organic molecules get accommodated inside a cube because of this strategy. We have accommodated a tetrahedron inscribed inside a cube. But as we have seen today in the forenoon session or in the earlier session of lattices, okay, see, cubic symmetry can endlessly, cubes can endlessly repeat in space, okay, and so this pattern can just proliferate in all directions. So, it is something like this, say, this rather so much localized the sp3 hybridized orbitals getting transformed into something more kind of international, something like the international currency. It can just be part of a very big lattice network of cubes. sp3 hybridized orbitals, say, they just take a ride, okay, riding on the cubes. So, they can, in other words, this strong but microscopic, say, covalent bond, okay, gets itself converted into a macroscopic proportion, and that makes the crystal so hard. So, the hardness of diamond has very much to do with this alliance between the tetrahedron and the cube. That is what I want to convey. Now, other examples are, see, the examples of this diamond structure as I indicated earlier. Carbon, that is diamond, silicon, they are the best known, germanium. See, of course, in carbon you have 2s2 2p2, the sp3 hybridized orbitals arise from this. In silicon it is 3s2 3p2, in germanium you have 4s2 4p2. They are isoelectronic, they have the same atmosphere, okay. Then you have another related structure, namely that of silicon carbide, okay. I will do that now. Suppose you have SiC, silicon carbide, which has a commercial name carborundum, which is the substance which is hardest next to diamond, second hardest substance. See, all these things, have the same electronic configuration and same crystalline structure, that makes this very hard. The only thing is, you have now two species of atoms, silicon and carbon. Okay. Look at this. Here you have all these crosses represent, you know, carbon atoms. Okay. Now, in silicon carbide, you have two species, silicon atoms and carbon atoms. The question naturally asked is, which of these sides should go to carbon, which of these sides should go to silicon. Okay. Remember, silicon and carbon have equal status here. Okay. There should be as many silicon atoms as there are carbon atoms. How will you do that sort of appropriation of locations to silicon and carbon? Okay. And again, before addressing that question, let us now address this thing. How many atoms of carbon are there in diamond in a unit cell? I think I can erase this part of it. This I will retain because that will be useful. See, how many carbon atoms are there associated with this? Apparently, you know, to the novice, it sounds a bit odd, because apparently, you know, 1, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 or so. Okay. And so, how will you decipher it? See, there are 18 carbon atoms. That does not make any sense, but one should remember, one should not ignore the fact that with respect to cubes, these things do not have the same status. See, as inmates of a cube, some of the carbon atoms are accommodated along the vertices, some others are accommodated on the face centers, still some others are accommodated well within the crystal without any sharing. In other words, these atoms are shared to different extents. So, one should consider that or take that into account, okay, to negotiate things. Okay. So, how will you proceed? Take the 8 corner atoms. You know that each corner atom is shared by 8 cubes. Okay. As far as this thing is concerned, see, this is shared by, say, 1, 2, 3, 4 below and 4 above. Okay. This is a typical corner atom. Each corner atom is shared by 8 neighboring cubes. So 8, see, this is shared by 1, 2, 3, 4 below and 4 above. So, its share is 1/8 to this cube, and there are 8 corner atoms, 1, 2, 3, 4, 5, 6, 7, 8, 8 into 1/8, contribution is 1. Now, as far as the face center atoms are concerned, 1 face center of top face, 1 bottom face, 2 left face, right face, front face, face behind, 6 faces. this is each is shared by 1 below, 1 above, 2. So, 6 into half, each say contributes only half of its might because of sharing by 2 neighbors. So, this is 3 and total, and then there is another species. See, now we have exhausted the 8 corner atoms and the 6 face centers. Now, what about this thing, the so called atoms located at positions like 1/4, 1/4, 1/4. It is unshared by any neighboring cubes. It is exclusively inside the cube. It gives its full might or full share. Okay. And how many are there? One along, say this one, say oriented along A, another along B, a third one along C, a fourth one along D, 4. So, these 4 atoms at the so called 1/4, 1/4, 1/4 positions are exclusively belonging to the cube. They remain totally unshared. So, you have 4 into 1 equal to 4. So, total number of atoms, effective total number of atoms inside the cube is 1 plus 3 plus 4 equal to 8. See, total is 8. Out of this, okay, you can just pair it like this, 1 plus 3 one side, another 4. See, so 4 plus 4, 8. Okay, so effectively there are 8 carbon atoms inside a cube in the diamond structure, which fully corroborates with the fact that you have an FCC lattice with a diatomic basis of 2 atoms. Okay, one at 0, 0, 0, the other at 1/4, 1/4, 1/4, because in an FCC lattice, see, you have corner atoms shared by 8 neighbors and face center atoms shared by 2 neighbors. So, effectively in an FCC lattice, you have 4 lattice points, 1 plus 3 equal to 4. And 4 lattice points, okay, each having a basis of 2 atoms, diatomic basis, one at 0, 0, 0 and the other at 1/4, 1/4, 1/4. So, you have 4 into 2 equal to 8. That is 8, which is 1 plus 3 plus 4 can be interpreted in different fashions equal to 4 plus 4. Again the same thing is 8 equal to 4 into 2. This is an FCC lattice with a diatomic basis 8. Okay. This is the actual situation 8. All come to the same point. You have basically 8 atoms in a diamond unit cell. Okay. This will give you the answer how to accommodate the silicon and carbon atoms in carborundum, in silicon carbide. It is evidently, say the simplest answer is you accommodate one species at the corners and face centers. So that you will have 1 plus 3, 4. You accommodate the other species at the unshared 1/4, 1/4, 1/4 positions. So that silicon carbide, for example, crystal will look like this. See, I will change the pattern now from, I am not redrawing this because it will take lot of time. I am based on this diamond unit cell, I am going to redraw the silicon carbide unit cell. As I told you, say corners as well as face centers should have the same species. The other 1/4, 1/4, 1/4 positions you will have the other species. So, this is see 1, 2, 3. See, this is silicon carbide. So, I will write here, this is silicon carbide structure. You can say it is an FCC lattice with a diatomic basis of dissimilar atoms, okay, namely the silicon occupying say the 0, 0, 0 positions and the carbon atoms occupying 1/4, 1/4, 1/4 position. You can as well say the other way around. You can say that it is an FCC lattice with a diatomic basis such that the carbon atoms occupy the face center as well as the corner atoms, corner positions, while the 1/4, 1/4, 1/4 positions are occupied by silicon. Either way, say you will get the same thing. And again, maybe if the students are adventurous, I will give you a very interesting homework for them. Okay, it will take some lot of time, but what with patience one can do. Just exchange. See, suppose you take this 1/4, 1/4, 1/4 position as the cube corner. What will happen? Okay, that with some patience one can do. See, you will get the whole thing inverted. You take this as the corner of the cube, the 1/4, 1/4, 1/4 position, then these things will be either along the corner or face centers. Then the corner atoms will be occupying the 1/4, 1/4, 1/4 positions of the new cubes. That is, they just they change roles. Okay, that is something which of course it will take a lot of time for me to demonstrate it here. So I won't attempt doing it, and the students are free to say explore this if they are adventurous enough. That is, the face center and corner atoms are on one side always, but the 1/4, 1/4, 1/4 positions will be just on the opposite side. If the 1/4, 1/4, 1/4 positions are changed to say corner or face centers, the corner and face center atoms will go to 1/4, 1/4, 1/4 positions. In fact, see, geometrically it can be methodically done, even though it will take some time. You take, for example, this is the best way is to invoke a Cartesian coordinate system, x axis, y axis, z axis. This is the origin 0, 0, 0, and this is 1, 0, 0. Okay. This is 0, 1, 0. This is 0, 0, 1. See, you have to put it like this. This is 0, 0, 1. Do not put any bracket or anything, because that will have a different meaning. It will mean the Miller indices of lines or planes, but here these are atomic coordinates. This simply means it has no x coordinate, no y coordinate, but one z coordinate. See, so x coordinate is exactly here. X coordinate means a crystallographic coordinate, y coordinate means b crystallographic coordinate. It is along this one. So, its a crystallographic coordinate is 0, b crystallographic coordinate is 0, but c crystallographic coordinate is 1. It is 1 unit away. Similarly, this is 1, 1, 0. You can verify this is 1, 1, 1. Say in a similar way, and this is say this point is 1/4, 1/4, 1/4. So, you can, with some time spent, you can just chart the positions of all the atoms. Then you shift your origin from 0, 0, 0, this is 0, 0, 0, to 1/4, 1/4, 1/4. So, you do the same thing on all, you will get a new set of coordinates, and you will see that, say, if this is shifted to, say, if this is the new 0, 0, 0, okay, this will be something like a phase center. Okay. Maybe you can just well, the only prohibitive factor is time. I do not want to do it, it will take a lot of my time. So, I will give it as a homework to the students to verify this thing, that is the phase center and the corner atoms will be always exchanging their positions to the 1/4, 1/4, 1/4 positions. Okay. And another thing which I can give as an exercise to the student is, see, there are two types of centering involved in cubic crystals. One is phase centering, phase center, okay. Then the other thing is body center. Okay. See, I will give a mathematical idea which one can easily develop. FCC into BCC equal to simple cubic. See, in fact, this has very deep group theoretical foundations, because simple cubic is, it plays the role of one identity element, because it has no complication at all. Okay. So, FCC is simple cubic by BCC, okay, or BCC is simple cubic by FCC. Since it is something like this, A equal to E by B, where E is the identity element, AB equal to E, we say that B and A are inverses. So, the inverse of FCC is BCC and the inverse of BCC is FCC. That is a very interesting idea one can toy with. Okay. In fact, that will be again, if we do reciprocal lattice, there is a very famous statement, the reciprocal lattice of FCC is BCC and the reciprocal lattice of BCC is FCC. Okay. It is again this result reflected in a different context. In this is as it happens in real lattice, the other thing happens in reciprocal space. Okay. Both amount to the same thing. Okay. It is, see, just numbers, you have, for example, 2 into 1 by 2 equal to 1. We say 2 is a reciprocal of half or half is a reciprocal of 2. Okay. 2 equal to 1 by half or half is 1 by 2. Okay. See, the question is, can we not have something of a geometrical nature which can imitate this numerical result? The answer is yes, something like this. Say these are geometrical, say, facts which imitate numbers. FCC and BCC are mutual inverses. Okay. Okay, I will just give you 2 homeworks problems which will easily convince you this thing. Okay. See, accommodate a diatomic basis of identical atoms at 0, 0, 0 and half, half, half. See, by this I mean body center. This is a vertex, this is body center. In oh, okay, accommodate a diatomic molecule, I mean a diatomic basis of identical atoms at once, I mean at 0, 0, 0 and half, half, half in an FCC lattice. The result is a simple cubic lattice. Okay, this is first problem. Second problem is accommodate a tetratomic basis, that is an atom having 4 atoms, I mean a basis having 4 atoms, tetratomic basis of identical atoms at 0, 0, 0, half, half, 0, half, 0, half, half. Okay, accommodate a tetratomic basis of identical atoms at, these are the 4 atoms, I mean the locations of the 4 atoms of the tetratomic basis in a BCC lattice. The result is a simple cubic lattice. Is a simple cubic lattice. Okay. Well, you can take it as a homework. See, if you are shrewd enough, you will see that it is, see what one is doing here, a diatomic base of identical atoms is equivalent to taking a body centered lattice. So, you multiply a body center BCC with an FCC lattice, you will get a simple cubic lattice. Accommodate, the second one is accommodate a tetratomic basis of identical atoms at this. That means you take, this is equivalent taking an FCC lattice, then multiply it with a BCC lattice. So, you will get simple cubic lattice. So, see here you have BCC into FCC equal to simple cubic. Here you have FCC into BCC equal to simple cubic lattice. So, you have BCC into FCC equal to FCC into BCC equal to simple cubic. Okay. This is a very interesting result which one can always take up as a homework. Okay. See, the important thing which I want to convey is the fact that BCC and FCC are, say, something like group theoretical inverses. Okay. Say in, for example, C3 inverse, and see you have in group theory C3 square equal to C3 inverse, C3 cubed equal to identity. C3 and C3 square are mutual inverses, because C3 into C3 square is C3 cubed, which is identity, or C3 square is C3 inverse and C3 is C3 square inverse. Okay. Same role is performed here. FCC plays the role of inverse of BCC and BCC plays the role of inverse of FCC. Okay, I think I will stop here. See, I have taken up only the diamond structure and related structure. There are so many other examples which are of interest on their own right, which I have not done here. Okay, so I will recapitulate what we have been doing. We have, in the present session on structure, I have illustrated the process with the special case of diamond, where I have done it using a special strategy, namely accommodating a tetrahedron inside a cube. Apparently, tetrahedron and cube are so disparate. So, but one can see that they can easily get fused, and the result is the famous diamond structure. And you have similar structures like that of silicon carbide. There are other materials like 3-5 semiconductors, which I have not touched here. They are also having related structure. Okay. Then again I just indicated the fact that BCC and FCC play the role of group theoretical inverses in to each other. Okay, that is all about it. Okay, and thank you all very much.